Hello, I'm Stefan Mabry, a PhD student at the University of North Dakota. Today I'll present the swarm intelligence algorithm, whale optimization. We will cover what this algorithm is, what problem it addresses, how it works, its strengths and weaknesses, and some real-world applications. So what is the whale optimization algorithm? Well, this algorithm is a population-based optimization algorithm. So instead of solving a problem with a single solution path, it maintains a set of candidate solutions and it evolves them over time. So that places it into the broader category of swarm intelligence. The key idea is that individual agents solve the problem by moving through the search space based on both their own position and the best known solution found by the group. So it's still a mathematical search process. We define the objective function, and the algorithm iteratively updates candidate solutions to either minimize or maximize that function. So there's no domain-specific logic built in. The algorithm doesn't really understand problems. It's just exploring the space efficiently as it's optimizing that evaluation function. And so it does that by that searching by being inspired by group hunting, like what humpback whales do. So why whale optimization? So first, it's a relatively simple model. It produces complex search behavior by the equations of being compact, but they generate non-linear movement through the search space. So that makes them kind of easy to implement, but still expressive enough that they can handle real-world problems. Second, it has an explicit mechanism for balancing exploration versus exploitation. So early on in the search, it behaves more randomly, and then as iterations progresses, it shifts towards refining around a best solution that it's found so far. And so that transition is controlled mathematically instead of through any type of heuristics. So third, it's flexible. The same core algorithm can be applied to very different problem types. So it can be engineering design, or it can be cloud resource scheduling, image segmentation, machine learning optimization. It tells you that it's not tied to a specific domain. It's instead a more general search strategy. And then finally, it's become the foundation of a large number of variant hybrids. People have extended this algorithm with mutation operators, chaotic initialization patterns, combinations with other algorithms like differential evolution. And so that's kind of a strength, but it's also a warning sign because not all of those improvements are justified, as we've seen in some survey papers I've used in citations here. So the reason to study the whale optimization algorithm is that it's a clean example of how modern swarm-based methods are designed, extended, and applied. And then those applications are to real-world problems, which is also why I selected this algorithm to explore. So what problems does it actually solve? So at its center, the whale optimization is trying to find the best possible solution to any given objective using a set of constraints. So that starts with the objective function. We define something measurable, which could be cost, error, energy use, or latency, and then we use that we use that for minimization or maximization, whatever direction we want that target to go. So we minimize or maximize the measure. So the algorithm doesn't really care what the function represents, really only how to evaluate it. So then we have the search space. That's the set of all possible solutions. And then in simple problems that might be small, but in most real-world problems, it's a large non-linear space. It's difficult to search efficiently. So that's where this algorithm is really useful. And then finally, this maps directly into real-world domains. So the same structure can show up in engineering design, cloud resource scheduling, machine learning, hyperparameter tuning, or image processing. So the inspiration for this whale optimization comes from humpback whale hunting behavior. So specifically around this bubble net feeding strategy. So there are three behaviors that matter in this process. So the first, the whales encircle prey once the target's identified. And second, they follow a spiral path to trap and attack that prey. And then third, when the prey isn't clearly located, they search more randomly across the environment. So the algorithm abstracts these behaviors into movement rules. So instead of whales, we have candidate solutions, and then instead of prey, we have the best current solution. And then those behaviors translate directly into three mechanisms: moving towards the best solution, updating positions using linear or spiral motion, and then switching between exploration and exploitation depending on the search state. So the next step from this inspiration is to formalize this into some equations. So let's walk through what these equations are doing. So each agent represents a candidate solution. So the vector x of t is the current position of the solution at iteration t. And then the x then represents the best solution that we've found so far. And then the distance term, the vector d, shows up in multiple places. So that's measuring how far the solution is from either the best solution or another randomly selected solution. And then it's the distance in the search space itself. The coefficients vector A and vector C control how that distance is used. Vector C scales the reference position, while vector A determines both the direction and magnitude of movement. So the key detail here is that vector A depends on the parameter A, which decreases over time from 2 to 0. And that drives the transition from that exploration to the exploitation phase. So on the left, we see the encircling equation. So that's where the agent's moving toward the current best solution. So that's the primary exploitation behavior. In the middle here, we see the bubble net equation. That introduces that spiraling update. So instead of moving directly towards the best solution that you do in a lot of other search functions, the agent's moving around it. So that helps refine solutions locally once the algorithm has identified a good region to search. And then on the far right here, we have the searching phase. So that's where the agent's moving relative to a random agent instead of the best one. So that allows the algorithm to explore new areas of the search space to avoid getting stuck at local optima. Early on, the movement is broader and more exploratory, and then over time it becomes more focused and refining around the best solutions that it's found so far. And what triggers that is this A solution, this little A vector that is moving from a value of 2 to a value of 0 over the course of the function. So this is the full algorithm. I'm not going to walk through it line by line, but instead I'll explain the whole flow as a whole. So we start by defining the problem. That includes the objective function, the bounds of the search space, the number of candidate solutions, and then the number of iterations. And then we initialize the population of whales, which are just candidate solutions, and evaluate their fitness. The best one then becomes our current reference point, x best. From there, the algorithm enters the iterative loop. At each iteration, we update the parameter a, which decreases over time, and that's from 2 to 0. The parameter controls how aggressively the algorithm explores versus refining. And then for each whale, we generate a set of random variables and compute the coefficients A and C. These determine how the whale moves through the search space. Then the key decision point happens at that point. So there's a probability value P, and that can be between 0 and 1. So when P is less than 0.5, the algorithm uses the encircling or random search behavior. And then if the vector A has a total value of less than 1, the whale moves towards the current best solution. and then that's the exploration. And then if A is greater than or equal to 1, we instead move relative to the random whale, and that's your exploration phase. And then if P is greater than or equal to 0.5, the algorithm switches to the spiraling update, so that that moves the whale around the best solution in a shrinking path. So that's the more refined local search. And so here P is random, which causes us to switch behaviors randomly to avoid hitting a local minima. There's other variations here that will make P adaptive or deterministic instead of random. But in our case, we're focusing on the random version. After updating positions, we then enforce the bounds of the search space, just to keep the function searching in valid areas. Then we reevaluate all the solutions and then update to the best solution we found if we find an improvement. So then the process repeats until we reach a maximum number of iterations, and then we return to the best solution that we found, and that becomes your final solution. So at a high level, the algorithm's repeatedly updating a population of solutions using controlled randomness and then structured movement to balance the explorations of the space with the refinement around good solutions. So now that we've seen how the algorithm works, we can evaluate it for where it performs well and where it breaks down. So on the strength side, the biggest advantage is simplicity. The algorithm is built from a small number of equations and parameters, which makes it easy to implement and adapt to different problems. It also has a built-in mechanism for balancing exploration and exploitation. So that's the parameters A and vector A, and then the probability P. Those three control how the algorithm transitions from a broad search to a local refinement over time. That structure is clean and it's easy to reason about. And then if you visualize it, how the humpback whales search, that makes it even easier to follow. Another strength is the flexibility, so the same algorithm can be applied to a wide range of optimization problems without changing its core logic. So that's why we see it used in engineering, cloud systems, and then machine learning. And then finally, it serves as a strong foundation for hybrid models. So because the update rules are simple, it's easy to integrate mutation or local search or other optimization strategies into this. On the weaknesses side, the biggest issue is premature convergence. The algorithm depends heavily upon the current best solution, so that if the solution is suboptimal early on, the population can collapse around it. Related to that, the diversity decreases over time, so as the parameter A shrinks, the search space becomes more localized, which can limit the algorithm's ability to escape local optima. It's also somewhat sensitive to parameter choices, so especially the population size and iteration account. So poor settings can reduce performance significantly. And then finally, there's a broader issue in the literature. As revealed in various review papers, there are many, quote, improved WOA variants. Yeah, that's not, like, not all of them are rigorously validated, though, is what the review papers have shown. So any type of reported performance gains over the base function should be interpreted carefully and reviewed more rigorously. So this diagram, this is a structured real problem in the cloud computing space. So on the right here, we see the microservices are coming from end user applications, and they can be any type of end user application that we've dealt with in reality. So these services are grouped and clustered and ranked based on workload characteristics. And then that information feeds into an optimization component. So in the paper here, reference number 6, which you'll see soon, so in the paper, they use the hybrid algorithm. So it's labeled here as FSWOA, or finely tuned sunflower whale optimization algorithm. So it's a conceptually WOA-based method, unlike the base algorithm that we covered earlier, which relies on stochastic movement. This approach introduces a more directed search and then it prunes out the weaker solutions. This improves the convergence speed, but it also reduces the generality and then also increases the risk of premature convergence. But in this case, the role here is the optimization of how the services should be assigned to available resources in the cloud. So on the left here, you can see that the outcome of the process is the algorithms driving the resource allocation and scheduling decisions across virtual machines and containers, while interacting with the system constraints like the SLA requirements or the resource availability. SLA being the service level, it's like how much time you have to respond to an event. So the diagram is showing where the WOA optimization algorithm fits into the real world microservice system. One more example of real world situations. This is a very different class of problem compared to the microservices we just saw. So here we're working with a physical system, which is a power grid. And then each node here represents a bus, and the connections represent transmission lines. So the goal is to determine how much power that each generator should produce, along with voltage levels and system settings, to minimize the cost and losses while maintaining stability constraints. And so that's a lot of constraints on the problem. That's a lot of various measures that you have, and they're nonlinear. So this is a nonlinear, non-convex optimization problem. That makes these traditional methods fragile and inefficient, but when you apply this whale optimization here as a global search method, it explores the solution space using the population-based search instead of gradients. It's more robust against local minima and those complex constraint interactions that we just talked about. It's really elegant how easily it can find solutions to problems like this. So the key takeaway here is that the same algorithm that we use in microservices can operate in a continuous, physically constrained engineering system as well, which I think is really cool. So this presentation walked through the whale optimization algorithm, what it is, how it works, and where it actually applies. So WOA is a simple population-based optimization method that uses structured movement rules to search complex solution spaces. It doesn't rely on gradients or strict assumptions about the problem, which makes it flexible across very different domains. We saw that flexibility in the applications. So in microservice scheduling, the problem is discrete and system-driven, focused on mapping services to resources under constraints. And then optimal power flow, the problem is continuous and physically constrained, where the goal is to balance cost, stability, and system limits. The same algorithm can operate in both settings because it only requires a way to evaluate the solutions themselves. So that said, the algorithm is not without its limitations. It can converge prematurely, especially in early solutions that are suboptimal, and its performance depends on how parameters are configured. It also doesn't guarantee global optimum, which is a common trade-off in meta-heuristic methods. So the value of the WOA is that it's practical, it's easy to implement, it's adaptable, and effective in complex optimization problems where traditional methods can struggle. In many cases, it serves as a strong baseline or as a component within a more advanced hybrid approach. Overall, the whale optimization is best understood as a flexible search strategy rather than a specialized solution, and its effectiveness depends on how well it's matched to the structure of the problem that's being solved. So these are the citations I used for this paper. 1 to 5 are the review papers and exploring what the algorithm is itself. So many of the graphics and images that you saw were taken from those, and I cited them along with the slides. And then 6 and 7 are your the problems, the specific domain problems that we saw. 6 being the resource scheduling in cloud computing, and then 7 is the power grid optimization problem. But if you want to do further reading, here are some more industry uses that I found that seemed really, really interesting to explore. So if you have any questions, you can normally ask here, but we're on the internet. So instead, this is my email address. You can get a hold of me on the QR code as well, which is my LinkedIn, or you can come visit me in Madison, Wisconsin. Thanks, and hope you have fun with this presentation. Have a good day.